Hello, my name is Scott Butcher. I'm the Chief Scientist at Meaglow. Today I'm going to be talking to you about our hollow cathode gas plasma sources, which are used in the semiconductor industry, but predominantly by the atomic layer deposition community. This is the outline of the talk. I'll give you a little bit of background as to how we started developing these hollow cathode plasma sources. I'll describe what a hollow cathode plasma source is, show you some of our designs, and then because people are most familiar with hollow cathodes when they are used as sputtering sources, I'll talk about metal contamination from these sources. And then finally, I'll end by looking at some of our newest hollow cathodes, which are made out of aluminum, and some of the results we've been getting with those. So some background into our hollow cathodes. We developed them not for ALD, but for CVD applications where we were seeing a lot of oxygen contamination from a plasma source. And in the ALD community, they have had this problem of oxygen contamination in their nitride films. And some of that's because they're growing very, very slowly. And there are many sources of oxygen contamination. There's just poor vacuum conditions, not using gas purifiers, not using a load lock. All these things will contribute. But when you get rid of all of those, you still have this contribution from the plasma source itself. And this is something that's been known for a number of years, but since back in 1989, that the plasma for inductively coupled plasmas and microwave plasmas will attack the dielectric lining of the plasma source and can release oxygen from that dielectric. And we've been working on this for quite some number of years ourselves and patented back in 2009 the hollow cathode solution to reducing oxygen in nitride films. And it turns out that people heard about this in the atomic layer deposition community, particularly Bilkent University in Turkey, who were trying to grow gallium nitride and aluminum nitride with their ALD system. And they'd done a few things to try and improve the oxygen content of their films. They put gas purifiers on the system, which you can see up here, and a load lock, and they turbo pumped their system and leak checked it, but they were still getting quite a few % of oxygen in their films. And anyway, they had a vacuum failure, and they took their system apart and found that the quartz liner for their ICP source, shown here, had actually etched through. So they suspected the quartz from that ICP source as being the source of oxygen in their films. When they replaced their ICP source with our hollow cathode, which is shown up here, their oxygen levels went down from greater than 4% in their gallium nitride to about 0.14%, and that's for polycrystalline material. So quite a marked reduction in oxygen, which allowed them to actually grow films that were useful for device purposes. And since then, other people have heard about our solution for reducing the oxygen content in nitride films, and we've sold quite a lot of plasma sources because of it. Over 60 plasma sources in 10 different countries, with some customers such as the NASA Jet Propulsion Labs, University of Texas, Dallas, US Naval Research, National Taiwan University, Hanyang University in South Korea, among others. And this is just showing some of our happy customers with their plasma sources. We convert many different types of system. Some results from the University of Connecticut. They've had some very good aluminum nitride deposition. I won't go into too much detail here, but very stoichiometric material. And some results from the University of Texas, Dallas, where they've been growing extremely good silicon nitride by ALD with one of our plasma sources shown here. But how do these sources work? So looking at the parallel plate capacitively coupled plasma source shown over here on the left, this is looking at the DC mode, but it's the same in this RF mode. Around the cathode, there's a sheaf region where most of the acceleration of electrons and ions takes place, and that's where most of your voltage drop occurs. And it turns out that if you put a hole in your hollow cathode, whose diameter is twice the sheaf width, then you trap electrons in that region and they resonate in there, creating a high density of ions and radicals. So this is the basis of the hollow cathode effect. And this is showing some of the RF characteristics of a hollow cathode plasma source. This particular plasma source was optimized to operate at 1 torr. But you can see here where we're showing characteristics over quite a wide range of pressures from 228 millitorr to 6,625 millitorr. And going up in RF power, initially what you see is an increase in the peak-to-peak voltage, which is what you would see in a capacitively coupled plasma source. But then as the hollow cathode effect occurs and you start getting plasma in the cathode holes, the voltage drops down significantly and the characteristic flattens out as you just put more and more power into your cathode holes. And this drop in voltage is characteristic of the hollow cathode effect. That's how we generally recognize it. So that's just talking about some of the advantages of hollow cathodes. We started out developing these and selling them to people because of the low oxygen contamination. But there have been other advantages such as high electron density, which I've spoken about, the wide pressure operation. I don't have time to go through all the positives of the hollow cathode sources, but one of the things I want to talk about is the scalability of the source. And that comes back to some of our designs, looking at our designs. And our first design, our generation 1 design, we were just using a whole lot of holes. But the problem with this sort of source was that if the holes had any contamination in them, or if you were outside the optimum pressure range, then you got uneven striking of the holes. And that was very hard to deal with. We had to limit the pressure range in which we operated quite severely. And also we had to clean the holes quite regularly, plasma cleaning between runs to make sure that they didn't get any buildup in them. So that was a non-ideal situation. But when we went to replacing ICP and microwave sources, because ICP sources are quite usually using a 1-inch quartz or alumina tube, quite small sources, we had developed very much smaller hollow cathodes, so barrel type structures with a few holes. Here you can see there's only 5 for this particular plasma source. And it's a very much longer cathode, and that length increases the probability of all the holes striking at once, because you're sort of stacking up a number of holes on top of each other, if you like. So this solution struck very reliably for a small area source. But one of the potential benefits of the hollow cathode that's quite highly touted is the ability to go to a larger area. So in our 3rd generation of design, we got around the problems with the 1st generation. This is showing a plasma source made of titanium that went to the NASA Jet Propulsion Labs. You can see the nitride on the surface here has turned the titanium gold. This is before this is showing the cathode wheel before it was used, still in its metal state. But there are a whole bunch of channels between the holes here. And what happens is when you strike a plasma in one of the holes, the channels conduct the plasma all the way around to the other holes. So you get very even striking. And that was our solution to allowing us with a solution which allowed us to go to larger areas. And there's some advantages in this now, because with ICP and microwave sources being very small sources, and they're small generally because you want to maintain a fairly constant flow of gas through them and not have backflow of metal organic into those sources, because if they get metal organic in the quartz, on the quartz dielectric, that can cause reflect the power back into the unit and cause it the quartz to eventually crack. It absorbs too much power at that metal surface. So they have these small, high densities tubes and the flow coming down from them, and then they're diluting that plasma down over a larger area for many of the solutions that are out there. So it's not ideal, but with our source, with the hollow cathode, having a large area source, you have a high density source at the same area as the substrate, which is quite a lot better in many situations. So this is our largest plasma source that we've developed using the this 3rd generation design. It's actually an aluminum source operating between 0.08 and 8 torr. And I'll show you how we got there in a second. First, I'm going to look at metal contamination from hollow cathodes because people are quite concerned. Most of what people are familiar with is hollow cathodes that are used for sputtering. And if you look at the DC characteristics of a hollow cathode, this is the region where you see a lot of the sputtering. You have to actually go up beyond the sputter threshold of the material in order to get it to start sputtering. And what we've been doing for these gas plasma sources is operate at a much lower power density down around here. So we're in a different regime entirely to a sputter source. So this just shows some of the things that you can do to minimize sputtering from your hollow cathode. Operating at the lower power density that I mentioned earlier is one way of doing that. Water cooling of the cathodes will actually help. Harder materials sputter less as well. And but when in situations where you can't really get away from the contamination levels that you want to see, you can use materials that are more compatible with the process. So for silicon, where almost every material will show a degree of sputtering that's sensitive for the silicon, the two materials that you'd want to look at are aluminum and titanium cathodes, because those two materials are more compatible with the silicon process. And so now we'll look at some experiments for the aluminum source that I just mentioned earlier. And what we were doing was we were modeling 2.5-inch diameter cathodes that we could scale up into the larger 12-inch size. Everything's scalable by area with these hollow cathode designs that we've developed. But you can see here, this is the bare metal aluminum cathode, and this is after having run the nitrogen plasma at 300 watts for a short period of time. And the cathode in this case is quite badly degraded as some sputtering has occurred. But when we worked out the power we had applied, which was 300 watts to these 2.5-inch diameter cathode, the equivalent for the 12-inch cathode would have been 6,900 watts. And we really only wanted to go to 3,000 for the 12-inch diameter cathode. So we could apply a lot less power and hopefully be below this this sputter threshold that we were seeing for the aluminum. And it turns out that when we were operating below 200 watts, the cathode was fine. It developed this nice bronze or coppery looking surface, which was probably a nitrided surface of the aluminum, and that helped protect it. If we then took the power up to 300 watts with this surface in place, we could operate without seeing that sputtering degradation we had seen previously. And this is showing some interesting effects for the nitrided film, the nitrided cathode. With the initial cathode, we saw an electron density down here for this particular set of conditions. This is measured with the bare metal, but the bare metal very quickly nitrides. At the end of this first measurement, it was almost fully nitrided, the cathode, and we redid the measurement, and we found that we were about half an order of magnitude higher in electron density for this particular set of measurements. It'd be a bit of variation from depending on how we were looking at these cathodes from one cathode to the next, but there was always an increase of electron density from the bare metal to the nitrided sample. And we understand this in terms of electron and plasma species recombination, because at the metal walls, you see a lot more recombination than you do at dielectrics. So this is indicating again that we had a aluminum nitride protective surface. So just conclusions now. We started out developing the hollow cathode sources because of the lower oxygen contamination that we could achieve with nitride semiconductors. But there are other advantages to these sources, including high electron density, and the new designs are allowing us to make them scalable to quite large areas. Aluminum hollow cathode sources, compatible with silicon. We initially didn't think they'd work very well at all, but it turns out that they can evolve a nitride surface on them that protects the underlying aluminum from sputtering, and that makes them usable. Thank you.